Okay, I think it is recording. Welcome everyone. So before we begin today's lecture, I just wanted to like like make certain assumptions about the course very clear. I'm still exploring how to do this remote online teaching without looking at the faces of the students. So to make things simpler, here are a couple of rules. So there are actually few of them. So the first point is like whenever there is a poll, please don't answer the poll in the chat. So just do the poll. And also I received some feedback that we wait a lot of time in the poll. It's like even if we spend 1 minute per poll, like it's taking a lot of time. So from now on, like whenever I start a poll, like we will do it only for 15 seconds. So like I will ask the question and then start the poll. It is your responsibility to answer within 15 seconds. So be active and make sure that like you click the option within 15 seconds. So this is to make sure that poll doesn't significantly delay the lecture. And also, a lot of you ask questions in the chat. So please remember that not all the questions will come to me. Like if the questions are simple enough, like which doesn't require interruption of the class. So we have one TA per lecture, like who is monitoring the chat, and the TA will be like going through the question and like answering your questions. Like if it is a quick clarification, but if your question is a little bit involved, I would recommend you to raise hand and ask me the question. You can also post it in the chat, but the TA will select questions to ask me while asking questions. And also to avoid continuous interruptions, like, so I'm going to try this from this lecture. So like I will stop at points for questions and I will, whenever I ask, is there any question? That is when like either you can raise your hand or the TAs can ask me the questions that you have. So that is regarding how are we going to handle Q&A. It's nice that you're asking a lot of questions, like, but at the same time, like we have to figure out a way to ask questions at the same time, optimally finish the lecture. Then there was also another point that I wanted to mention. Yeah. Okay. So some of you have already done some machine learning. Like some of you might have practical experience. Some of you might have done probably a different machine learning course and you're in the lecture. So here's my request. So when I ask a question, I expect you to answer the question based on like whatever has been taught so far. So like the best example is like, well, like in the last lecture when I asked, how can we solve classification with whatever we have learned so far? Like, so whatever we had learned so far was only linear regression, right? Like, so at that time, I don't expect you to say, for example, we could solve this by using a neural network. So if you have extra machine learning exposure, I would recommend you to erase them and start from scratch. And like, so like when you ask, at least when you answer questions, like the answer should be based on what we have covered so far, so that we can progressively build on top of what we have learned. Okay, so that is like a couple of things to make sure that like the lectures go smoothly. Let's get started. One second. I'm trying to share my iPad. And I don't see my iPad to be shared. Sorry, just a second. Okay. Okay. So just to remind ourselves, like, so where did we stop previously? Like like in the last few lectures, like, so we looked at, like we started with basic linear regression. And then like we also looked at how to do polynomial regression. And then like we discussed the general machine learning pipeline. And we also started with classification, like where we started with this toy data set, which is blue versus orange. And at first we applied the linear regression model that we already learned. So which is what I mentioned here as least squares, right? Like, so this is a solution that we have. And then we also learned a new algorithm last week, which is nearest neighbors. So the basic idea in nearest neighbors is like, given a new data point, like you would find k nearest neighbors for this data point and take a majority voting among these neighbors. Like if you have 7 out of 10 neighbors being blue, then probably you are also blue. So that was the principle behind nearest neighbors, right? So now I just want to like make a note here that just like how we are using least squares for both regression and classification, we could also use nearest neighbors for regression. So simply what you would do is, given an x, you will find k nearest neighbors and take an average of their predictions to be the real prediction for this particular like example, right? Like, so that is how you would use nearest neighbor for regression. Okay, so now let's quickly compare the characteristics of these two algorithms that we have learned. So the first algorithm is least squares, and the second algorithm is nearest neighbors, right? So as we can see from these figures, you can see that in the case of nearest, like least squares, the decision boundary is very smooth. It's just a line, right? And on the other hand, for nearest neighbors, the decision boundary is like a bit wiggly and it depends on a handful of points. For example, in this case, maybe I will use a different color. So in this region, okay, that color is also not working. Okay, let's try this. Okay. For example, in this region, you can see that there are a few blue points which started dominating this local region. So you have a small blue region within the orange region, right? So basically, in the case of least squares, the decision boundary is very smooth. On the other hand, in the case of nearest neighbors, the decision boundary is wiggly and depends on a handful of input points. Okay, so in some sense, least squares is more stable. So you will not have such like tiny regions formed in least squares, like because of addition of few blue points, right? Like on the other hand, K and N, like the nearest neighbors, is less stable because I could, for example, add just a bunch of blue points here, and this region will become blue, right? So this is less stable. Okay, so what are the assumptions that these two different algorithms make, right? Like, so least square makes this assumption that the decision boundary is linear. On the other hand, K nearest neighbor makes a different type of assumption. It assumes that the class distribution is locally smooth. Just if you look at the local region, it's going to have the same class distribution, right? So this model assumes that the class distribution is locally smooth. Okay, so in terms of terminologies that we will learn in the next few lectures, least squares is a model which has high bias. and low variance. It has high bias because it's strongly biased about the fact that the decision boundary is linear, right? On the other hand, nearest neighbor does not have such bias. Like for nearest neighbor, like you can draw any type of decision boundary depending on the data. So this has low bias. But because it has low bias, by just adding few points, I could change the decision boundary, and hence this has high variance. Okay, so now we have these two types of algorithms. They each having different characteristics, right? Like so, in fact, like we are going to learn many more algorithms in this course, and each of these algorithms are going to have their own characteristics. So now the question is like, which is the best algorithm, right? Like so, is there one specific algorithm which is like universal, or like which is the best algorithm that could be applied for any data? So this is some question like which we will get back to like for every few lectures and discuss the implications of answering this question. Okay, so maybe I would take a couple of questions here before we start with today's lecture, which is on statistical decision theory.
Okay, perfect. I had one question only. So the question is as follows. What if you use high order polynomial in least squares? Will the assumption for the decision boundary still be linear?
Well, that's a good question. So no, it's like, so when I say least square, I just mean the linear regression here. Like when you use higher order polynomials, then the decision boundaries are going to be non-linear, right? Like, so then like, as the degree of the polynomial increases, you're going to get more and more non-linear decision boundaries. But remember that even in that case, least squares is making a strong assumption, because it says that, for example, if you choose a 20-degree polynomial, it is confident that the shape is 20-degree polynomial, right? Like so that's not the, in that sense, nearest neighbor is very flexible. It's completely data dependent.
Perfect. Only question I had.
Okay. So now in this, okay. So sorry.
We actually have another hand raised just now.
Yeah, sure. Yeah.
So, Guy Hermin.
Yes, thank you. I have a question regarding the least square. I mean the linear regression. You say we have high bias and low variance. What if the assumption are true? In this case, then we don't have high bias.
That's a good point. So if the assumption happens to be true for this data set, then that's the best algorithm, right?
Yeah.
But if but in real life, like we don't know if the assumption will be true for the problem in hand.
Okay, so since we don't know if the assumption will be true or not, can we say that the linear regression is high bias, low variance?
Okay, so that's also a good question. So again, like depending on like our assumptions that real life problems are complicated. So we say it has high bias because we think that maybe like most of the real life problems are not linear, right? So in that sense, it has a very high bias.
Okay, thank you.
But we will have like a detailed discussion on bias and variance probably in a couple of lectures.
Okay.
So this is just like I'm just putting it here for your thought, so that you can think about it. Like we will have a detailed discussion later.
Okay, thank you.
Okay. So we will start with like today's lecture. So we are going to discuss about statistical decision theory. Okay. So the goal here is to understand like the general principle behind these prediction problems, regression and classification. Okay, but let's start with regression. Okay, so we are going to assume that we have input x, which is some p-dimensional, okay, to be a real valued random input vector. Okay, similarly, y, the target, is a scalar real value, so it's a real valued random output variable. Okay, so now when we think about the data that we have, the problem in hand, like which is like given some x, you want to predict y, right? So now this problem, like in probabilistic sense, comes from some joint distribution, probability of x comma y. Okay, so this is the joint distribution of x and y. Okay, so now the goal in regression is to find a function f of x for predicting y given values of x, right? That is what our goal is. So to achieve this goal, we often construct a loss function which takes both the true prediction and like true target and the model's prediction as example, like as input, right? So this is the loss function for penalizing the errors in our predictions. And the most common loss function, in fact, the only loss function that we have seen so far in this course, is the squared error loss, right? So L of y comma f of x is given by y minus f of x the whole square, right? So now this is the loss function. So now first we will ask this question, which is, what is the expected prediction error for a model? Okay, so now if both x and y are random and we are interested in predicting y given x, now what is the expected prediction error? So we are going to define that as expected prediction error of some function f is expectation for y minus f of x the whole square, right? So this is an expectation over two random variables x and y. So let's expand this expectation. It is basically integral y minus f of x the whole square probability of x comma y dx dy, right? So let's say integral x integral y. So I'm going to do a little bit of like restructuring here. So integral over x, integral over y minus f of x the whole square. So I'm going to take this joint probability p of x comma y and make it p of y given x p of x. Okay, and I will also bring dy inside, so this becomes d of dy p of x dx. Okay, so now look at this integral. Can someone tell me what is this integral by raising hands? Is anyone raising hands?
No, not yet.
Okay, so what is this integral? Okay, so someone is typing. Remember that when I say raise hand, you should not answer it in the chat, but okay, this time it's fine. So it's an expectation of y given x, right? So this is basically the formula for expectation with respect to y given x. So this becomes integral over x, expectation y given x, y minus f of x the whole square, okay, given x is equal to x. This is y given x, right? And you have p of x dx, right? So now look at the outer integral. Now this integral is expectation with respect to p of x, right? So this becomes expectation over x, expectation over y given x, y minus f the whole square. I'm going to call f of x as f for ease in writing, given x is equal to x. Okay, so now this is what the expected prediction error for some function f is. Okay, so now looking at this function, we first notice that this term is given some x, right? So in some sense, it suffices to minimize this EPE pointwise. So if I minimize this for every x, then like whatever function, like whatever f that I get, which minimizes this particular expected prediction error, is the best algorithm, right? So in this case, this becomes like the f star, the optimal algorithm for regression that we are looking for is given by argmin of f, expected value of y given x, y minus f the whole square given x is equal to x. Okay, so now, so this is to answer like our question, like which is what is the best algorithm to solve. We'll consider for classification too, but for now, what is the best algorithm to solve the regression problem, right? Like so we have seen linear regression, we have also seen k nearest neighbor. Now, what is the best algorithm to solve regression problem? So this simple, like short derivation tells us that the best f that one could aim for a regression problem is something which minimizes this expectation with respect to y given x. So there was a hand raised. Maybe I can answer that question.
Yes. So
Yes. Hello. So,
Yeah.
can you hear me?
Yeah.
Okay. I'm sorry. Can you please repeat what is the PRXY, please?
Okay. So PRXY is basically the joint distribution of x and y. So you have this problem which is predicting x from y, and we assume that the data points come from a joint distribution x and y.
Okay. Okay. Thank you.
Okay. So now this is what we are looking for, right? So now we could actually solve this optimization question and see what is the answer. So to do that, let me probably first copy this to the next page. Okay. So this is what we are going to solve now. Okay. So how do we solve this problem? So we are interested in finding the minimum for this function. So we know the procedure. You differentiate it, set it to 0, you find the minimum, right? So we are interested in doing dou by dou f of expected value of y given x, y minus f the whole square given x is equal to x is equal to 0, right? So now how does this work? So we can actually expand this square. So this becomes dou by dou f, expected value of y given x, just the y square given x is equal to x, okay, plus f square. Expectation is with respect to y given x. There's no y given x in f, so it's just f square, minus twice expectation of y given x is equal to x multiplied by f. The whole thing equal to 0. So all I have done is like expanded a minus b the whole square. Okay, it's a square plus b square minus 2ab. Okay, so now we can see that we are differentiating with respect to f, right? So this term becomes 0. So when you differentiate f square, you get 2f. Minus when you differentiate 2 something x, you get 2 something, right? So 2 expected y given x is equal to x is equal to 0. Okay, so now f star is given by expected value of y given x, y given x is equal to x. Okay, now this is the optimal function that we are looking for, and this function is known as the regression function. Okay, so what does this function tell us? This function tells us that at any point x, the conditional mean is the best prediction that you could achieve. So this says that the conditional mean is the best prediction. Okay, remember, if the measure is squared error. So we started with squared error function and we asked this question: what is the best algorithm that could minimize this squared error function, right? Like, so what would be the optimal function? And here, like, we have the answer, which is basically the optimal function is the expected, like it's a conditional expectation, like it's like conditional mean for y, like where it is conditioned on any x, right? So okay, so now this is the optimal function. The first question is like, can we ever, like, if we have the optimal function, like, why not use it, right? Like, why do we use linear regression or k nearest neighbor? Any hand raises? Okay, Bruno, I think Lawrence will unmute you.
We don't have
Yes.
data for every x.
Okay, we don't have data for every x. Okay, that is right. The other way of saying that is we don't have access to this distribution function. So we don't have access to probability of x given y, right? So only when you have access to this function, you can compute this expectation of y given x. So for most of the real life problem, you don't have access to all possible x and y, so which is basically captured by the distribution, right? So we don't have access to the distribution. So in reality, we could never find this optimal function f star. Okay, so now this is why we are studying about different algorithms which are all trying to optimize, which are all trying to approximate this true function f star. Okay, so now let's start with nearest neighbors. So what is nearest neighbors doing? So how is it approximating this function f star? Okay, so nearest neighbor, what is nearest neighbor doing? Now remember that the equation for nearest neighbor is you take an average. So we are in a regression setting, so we are going to take an average instead of majority voting. You take an average of all the yi's of the neighbors given xi belongs to some neighbor in the kth neighborhood of x, right? So you take k nearest neighbors, you take an average of those, the yi's, and that is your prediction by the nearest neighbor. So now let's try to compare this with the true function f star. Okay, so the true function f star is expected value of y given x, y given x is equal to x. Okay, so now this is what nearest neighbor is doing, and this is what the optimal function that we always want to reach, right? Okay, now we can see that nearest neighbors is making a couple of approximations here. Okay, so the first approximation is, instead of having expectation, nearest neighbor is like averaging over the sample data. So basically expectation is approximated by averaging over sampled data. Okay. Similarly, it's also making a second approximation, which is basically instead of conditioning on the input x, it is conditioning on the neighbors of x, okay, to get some statistics. So basically conditioning at a point is relaxed to conditioning on some region which is close to the target point. Okay, in some sense, since we don't have any information about this x, we are dependent on the neighbors of the x to make our prediction. Okay, so now this is what nearest neighbor is trying to do. Okay, so now first let's understand that this is a very powerful algorithm, because the first note, for large training sample size n, okay, the points in the neighborhood are likely to be close to x. So as I get millions or probably billions of data points, when I look at the nearest neighbors, they are going to be as close as possible to the x. So in that sense, this particular approximation will go away. So when I have a lot of data points, like, then the approximation will get better and better. Okay. Similarly, note 2, as k gets larger, okay, then the sample average that we are doing will get more stable. Or in other words, when I look at a lot of neighbors, like as k increases, this average is going to be very close to the true expectation. Okay, so under some mild regularity conditions on the joint distribution, we can actually show that as both the number of examples and the k value tends to infinity, such that k by n tends to 0. It means n first tends to infinity faster. So you get way more examples, that n becomes infinity faster. In that case, nearest neighbor would tend to the true expectation of y given x is equal to x. So when you have infinite amount of data, then nearest neighbor is going to give you the optimal function that you are looking for. Okay, so now this looks like we have a universal function approximation, right? So nearest neighbor seems to be a powerful algorithm that, like, given a lot of data, it's going to approximate the function that we are looking for very well. It is going to do this for any function, right? So in some sense, we could consider that as a universal function approximator. But there is a catch here. So remember that, like, every time I say it could approximate the function very well, I also say that when given infinite amount of data, right? Like, so this method requires a lot of data. Now, this brings us to one of the major issues in machine learning, which is basically like problem with high dimensionality. Like, so when I have, I don't know, like when I have like 100-dimensional data, 1,000-dimensional data. So like when I have like high dimensional data, what are the struggles that these algorithms are going to face? Specifically, we will look at what will local method like nearest neighbor, which is looking at the neighbors, right? So local methods will do in high dimensions. Okay, so now to explain this, like, we are going to consider the data points lying in a unit cube. Okay, so let me see if I have the cube ready. Okay, so now, my data point lies in this unit cube. Assume that all the data that we have is in this unit cube. Okay, now let us also assume that we consider neighbors to be like the smallest unit, like smallest cube around you. Okay, so now this is one neighborhood example. Okay, so we are going to consider, okay, now this is a 3D example. Similarly, you could consider, if you have 100 dimensions, you could consider a 100-dimensional hypercube. It's just that we cannot visualize it. Okay, so now consider inputs uniformly distributed in a p-dimensional hypercube. Okay, similarly, we are considering a hypercubical neighborhood. Okay, and around a target point, given a target point, I want to consider the hypercubical neighborhood to capture R fraction of the observations. For example, like what is the neighborhood required to capture 1% of the observation or 10% of the observations and so on. Okay, so now this corresponds to the fraction R of the unit volume, right? So now in some sense, the expected edge length, let's call that as EP of R, is given by R power 1 by P. Now, this is based on the fact that volume of a hypercube is R power, like whatever side power P, right? So we are interested in finding the length, so it's a reverse. So for example, like if we are in 10 dimensions, okay, and we want to see what is the length required to capture 0.01, which is 1% of data. Now, if you substitute this, you can get the value, which is 0.63, okay. Similarly, in 10 dimensions, if I have to capture 10% of the data, it's 0.80. Okay. Now, what does this tells us? Like this tells us that, remember that the entire range of input is only one. It's a unit cube, right? So you need to cover 63% of the range to capture even 1% of the data. Similarly, you need to cover 80% of the range of the X to cover 10% of the data. Okay, so now this highlights the problem that you would face with these local methods in high dimensions. So this is just 10 dimensions, right? Like in 10 dimensions, suddenly local is no more local, right? Like so covering 63% of your data set is not a local method, right? So these methods are no longer local. So now obviously, like if you try reducing this length to cover only like smaller portion of your range, then you're going to have a lot of variance, right? So now this issue, like as you can see here, like for example, this tells you what is the distance that you should cover, like to cover this fraction of volume for different dimensions. So one dimension in one dimensional X, 2-dimensional, 3-dimensional, 10-dimensional, right? So you can see that as the dimensionality increases, very soon you would require a lot of examples. Like so exponential number of, you need an exponential coverage as dimensionality increases. And this is just 10 dimension. Like so in reality, like we would often work with 100 dimensions, 1,000 dimensions, sometimes even 10,000 or 100,000 dimension data. So when you have such a high dimensional data problems, then k-nearest neighbor is probably a very poor choice of algorithm, simply because it doesn't scale up to higher dimensions, right? Like so this phenomenon of like local methods struggling in high dimensions is known as curse of dimensionality. The phrase often attributed to Bellman. And this is one of the serious issues. And in fact, most of the algorithms that we see in this course will help us to solve this curse of dimensionality and scale up things that we are learning to higher dimensions. But before we continue, I would like to give one quick warning, which is throughout this course, like we will be focusing more on 2-dimensional, 3-dimensional examples, simply because we can easily visualize them and it gives an idea of how the algorithms work, okay? But in practice, even in your assignments, you are going to work with n-dimensional data sets where n is typically at least 100, like sometimes even very large, 10,000, 30,000, okay? So always remember that our intuitions often break down in higher dimensions. That is why it is extremely important that you also have some practical knowledge complementing the theory that you are learning, which is exactly what your assignments and competitions are focused on. So one way in which like one of my AA profs at IIT like taught about this curse of dimensionality or the problem with higher dimensions is this. Like, so I want all of you to close your eyes and imagine the distance between 10 and 20. So just imagine a line, like try to find the, try to visualize the distance between 10 and 20, right? Now, on a relative scale, try to measure the, visualize the distance between 10 and 100. Okay, so now try to visualize the distance between 10 power 20 and 10 power 21. Whatever visualizations that we could think of, it is going to be orders of magnitude wrong, underestimated than like what could actually be the difference between 10 power 20 and 10 power 21. It is simply because we cannot handle those high dimensions even ourselves, right? Like so like the general message here is like anything that we learn here, like always remember that you should translate these 2D, 3D examples to high dimensional examples, and you can do that by only by applying these algorithms to high dimensional data. Okay, so any questions?
Yes, there was a question in the chat. So it says, what if we use multilinear regression dealing with big data? In this case, can we say these two models are comparable?
Okay, so what is, I'm not sure what does the student mean by multilinear regression. Maybe, I think he raised his hand. Maybe you can unmute him.
So my question is using, so let's say K linear regression, is it comparable with K nearest neighborhood?
Yeah, so well, that is another algorithm, right? Like, so you could mix these two algorithms and like have K nearest neighbor, but when you go to the neighborhood, then you do a linear regression there. You could do that. That's a good suggestion. So that would help you a bit to solve this issue, but it's not going to completely solve the issue.
So I think for now is the only question.
Well, okay. Well, if you guys want spoiler, the spoiler is there is no such universal learning algorithm. So like every algorithm that we are going to discuss in this class will have some disadvantages, and like not everything is applicable in every other place. So this is often explained by using what is known as no free lunch theorem. It literally means there's no free lunch, right? So we will discuss more about no free lunch theorem and other stuff probably like towards the end of the course. Okay, so before
just one comment, sorry. I think some students mentioned the scratching sound when you were talking. Can you like solve this easily?
Okay, that might be because of my chair.
Yeah.
Okay, I will try not to move. Okay, so before we go for a break, so I want to also discuss about what is linear regression doing. Like, so we spent a lot of time in discussing how is K nearest neighbor approximating the optimal function, right? So now what is linear regression or least square doing, right? Again, so let's remember f star is given by expected y given x. Y given x is equal to x, right? Okay, now what is linear regression doing? So linear regression is basically something like W transpose X or X transpose W, whatever way you call it, right? So now these two look very different, right? Like, so like at least in nearest neighbors, like we can actually say okay, the expectation is approximated by the average. Conditioning on X is approximated by the neighborhood, right? But these two look completely like they're very different, right? So linear regression is an example of what we will call as a model-based approach. Okay, so basically, linear regression is a way of specifying the model for the regression function and then using that model. So in this case, the model is essentially the parameters W, which is given by expected value of X transpose inverse expected value of XY. Okay, so remember that, note that we are not conditioning on X. Rather, we are using the knowledge of the functional relationship to pool the values, right? So in some sense, we are going to discuss a lot of algorithms in this course, which are all model based in the sense we will come up with, okay, I think maybe it's the microphone rubbing my shirt. Okay, I will fix it after break, sorry. So in some sense, like, we are going to discuss a lot of model-based approaches in this course, like which is where the typical recipe is we will define a model. So when you define a model, in this case, it's a linear regression model. We could define other complex models that we will see very shortly. Like every model is going to make some assumption, and then you estimate the parameters of this model, right? So this is very different from like what k-nearest neighbor is doing. Okay, so now this brings us to the important point that we should always remember, which is the assumptions made by any algorithm. Okay, so in the case of linear regression, okay, it assumes that f of x is well approximated by a globally linear function. Okay, on the other hand, k-nearest neighbor makes a completely different assumption. It assumes that f of x is well approximated by a locally constant function. It says that locally, in the neighborhood, the class would be the same, right? Now, these assumptions that every algorithm is making, right? These are known as the inductive bias of the model. Okay, so every algorithm is going to have some inductive bias, and whenever we introduce a new algorithm, we will also discuss about, okay, what is the strongest assumption. So inductive biases are basically the strongest assumptions made by that particular model, and like every time we see a new algorithm, we will discuss, okay, what are the inductive biases of this model. Okay, so one last thing before we break, which is this whole discussion on decision theory for regression was based on L2 loss, right? And I also told you that that is the only loss that we have seen in this course. We will see several other loss functions in the future, but let me just introduce one more loss function, which is L1 loss. So which is basically, instead of y minus f of x the whole square, it is just y minus f of x. Okay, so now L1 loss is given as expected value of y minus f of x. Okay, now what happens, like what will be the best, like, or optimal function which could minimize this loss? We are not going to do the same derivation again, but if you do the derivation, you will find that the f star for this loss is given by another estimate, which is median of y given x is equal to x. So instead of being conditional mean, it's going to be conditional median. Okay. Now this is a different measure, and this is usually more robust than conditional mean. But historically, L2 loss is more popular. You will see L2 loss almost everywhere, not L1 loss, simply because of the discontinuities in the derivatives. Like when you differentiate L1 loss, see that there is a modulus here. So like you're taking the absolute value, which is not differentiable, right? So that's one reason why L2 is more popular than L1. Okay, so there is a question: is there such a thing as non-linear regression? Yes, we will discuss about it like in the next half. So, okay, now we will take a short break and resume at 1:45. I'm going to stop the recording.